Hi everyone, welcome back to my channel. In today's video, we are going to learn about one of the powerful supervised learning algorithm, that is support vector machine, also called as SVM. Now let's start our video. What is support vector machine or SVM? It is an algorithm that classifies data by finding the optimal hyperplane which maximizes the margin between different classes. The larger the margin, the better the model performs. A support vector machine is a supervised machine learning algorithm used for classification and regression tasks. Now let's see how support vector machine work. For example, we have a data set of two classes. One is blue, another is orange. Now we have to find out our new data is either blue or orange. But we can have many decision boundaries like these lines. Therefore, we have to find which is the best decision boundary. For that, the main objective of SVM is to find the maximum distance from both the classes, and that is our optimal hyperplane. There are some key concepts of SVM. One is hyperplane, support vector, margin, hard margin, soft margin, kernel, C parameter, hinge loss, dual problem. Now let's discuss each of them. Hyperplane. It is a decision boundary that separates different classes of data. Here, the green line is a hyperplane. It is represented by the equation Wx plus b equals to 0 in linear classification. In 2D, it is a straight line, whereas in 3D, it's a plane. But in higher dimension, it is called the hyperplane. Support vectors are the closest data points to the hyperplane, and they define the position of the hyperplane. Margin. It is the distance between the hyperplane and support vectors, or the closest data points from each class. SVM tries to maximize this margin to make the model more robust. Hard margin. In hard margin, there is no misclassification allowed. That is, it only works if the data is perfectly separable. Soft margin. In soft margin, it allows some misclassification for better generalization. It is a technique to handle non-linear data by transforming it into a higher dimension. C parameter. It controls the trade-off between maximizing the margin and minimizing classification error. Small c means wider margin, that is more classification. Large c equals to narrow margin, means fewer classification. Hinge loss. It is the function that SVM uses to measure error. Loss equals to 0 if point is correctly classified and outside margin. Loss is greater than 0 if point is misclassified or too close to the boundary. Dual problem. It is an alternative way to solve SVM using optimization. Here, only support vector matters in this form, making SVM efficient. Workflow of SVM. First is input data, that is to collect and prepare the dataset, such as features and labels. For example, temperature and humidity are the features, whereas buy ice cream is the labeling. Next is feature scaling. SVM is sensitive to scale of the features, thus it has to normalize the data so all the features contribute equally. The third is choosing kernel function. It decides how to separate the data. Linear kernel is used if the data is linearly separable. Polynomial or RVF kernel is used if the data is non-linear. Setting parameters. C regularization control margin versus error trade-off. Gamma controls the influence of each data point for RVF control. Training the model. SVM finds the optimal hyperplane that maximizes margin, and it identifies the support vectors that define the boundary. Prediction. In prediction, it uses the trained SVM to classify new data points, for example, to decide which side of the hyperplane they fall on. Evaluation. It measures the performance with metrics such as accuracy, precision, F1 score. Therefore, this is the workflow of SVM. Now let's move to the another chapter. Types of SVM. Linear SVM, non-linear SVM, SVM for regression. Linear SVM is used when the data is linearly separable. That is, when the data points of different classes can be separated by a straight line or a hyperplane. Non-linear SVM, it is used when the data is not linearly separable between two classes by a straight line. Nonlinear SVM applies the kernel functions to transform the data into higher dimension where it can be separated. SVM for regression. Instead of classification, SVM can be adapted for predicting continuous values, for example, predicting house prices. Why SVM matters? Robust to outliers. SVM focuses only on the closest points, so noisy points far from the margin don't affect the model too much. Effective in high dimensions. SVM works very well in high dimensional space, that is, when the number of features are large, even if there are few data points. That's why it is great for image classification. Versatile. SVM can handle nonlinear data using kernel functions like RVF and polynomial. Maximizes margin. SVM reduces the risk of overfitting by finding the hyperplane that maximizes the margin, and it also improves the prediction on new data. Applications. The applications of SVM are in various fields. Some of them are in bioinformatics. SVM can be used for classifying genes or DNA sequences, such as predicting protein function from genetic data. Face recognition. It can be used for verifying faces in security systems. Text classification. SVM can be applicable for classifying emails as spam or non-spam emails. Image classification. SVM is used for classifying objects in images, such as detecting tumors in MRI scans. Handwriting recognition. It can be used for recognizing digits or letters from scanned documents. Okay, that's all for support vector machines or SVM. We understand that SVM is a supervised learning algorithm that finds the best boundary between classes, and it works by finding support vectors and maximizing the margin. It can be used in real life scenarios such as medical diagnosis, spam detection, and so on. Thank you for watching. If you like this video, do not forget to like, share, and subscribe my channel. See you in the next video.